Bienvenido a un nuevo evento de Cátedra Europa.
Good morning. On behalf of the 24th edition of Cátedra Europa, we welcome to the lecture From Volcanoes to Green Mining, Volcanismo y magmatismo, su aplicación en la formación de fluidos hidrotermales y minería, for which we have the special participation of Dr. Jonathan Blundy, Dr. Catherine Cashman, and Dr. Mary Edmonds. We will now leave you with Professor Paula, who will be moderating the session.
Okay, welcome to this session from Volcanoes and Green Mining. So before to start the whole presentation, I would like to introduce the lectures. So the first presentation will be carried out by Catherine Cashman. She is a geologist from Melbourne College, USA. She has a master's degree from Victoria University in New Zealand and PhD in geological science from Johns Hopkins University in USA. Currently, she is a volcanologist and acts as a professor at the University of Bristol in UK. She's interested in using the products of volcanic eruption to determine the process that formed them. Her work has encompassed all types of volcanic activity and all 7 continents, and has employed tools that include field geology, analytical petrology, experimental petrology, fluid mechanics, seismology, remote sensing, atmospheric science, and statistics. More recently, she has been developing collaboration with paleoclimate statistics, historians, archaeologists, and artists to explore the range of interaction between volcanoes and human population in space and time. Then will be the presentation from Mary Edmonds. She's a professor in volcanology and petrology from the University of Cambridge in UK. She's interested in the behavior of volatiles in magma, in particular, how volcanoes gaseous emission can be used for monitoring and for understanding the hydrothermal ore deposits and the condition of magma stored in the crust. She's recently co-lead the reservoirs and fluid community of the Deep Carbon Observatory, tasked with quantifying the fluids and carbon into and out the Earth interior, and is involved in UK Research Council fund projects, observing volcanism from space and understanding the transport of chemical transformation in volcanoes plumes. She received a AGU John Simpson Medal in 2020 and in 2017 ABCEE Warden Medal. We finalized the session with the Dr. John Blundy. John is interested in all the things magmatics, from magmatic generation in the crust and the mantle to active volcanoes and hydrothermal mineralization. His approach is his research using a combination of field observation, thermodynamics, microbiome analysis, and high pressure temperature experiments. He has worked on volcanoes around the world, including East Caribbean, Altiplano, Mexico, Cascades, Bentiu, Antola, and many others. Since 2010, John has become engaged in industry fund applied research into the origin of porphyry copper deposits from volcanoes and petrology perspective. After 31 years at the University of Bristol, he moved to University of Oxford in July 2020 as a Royal Society research professor to work on a project entitled From Volcanoes to Green Mining, rethinking the igneous geochemical cycle. So let's start with Dr. Cashman. At the end of the presentation, we have the session questions, so please write your questions in the toolbox. Thank you.
Okay, well, thank you very much for this really wonderful opportunity. And let's see, I'll share my screen. Can everyone see that?
Yep.
Yep. Okay. So I'm happy to be the lead-off talk in this Volcanoes to Green Mining session. And I'm going to take you from magmatic systems to volcanic eruptions. So what I really want to show you is that in the past 2 decades, the focus of magmatic studies has shifted from the upper crustal magma chamber to the entire crustal magmatic system. And this has been a big shift that has really altered the ways in which we view not only magmatic systems, but also the conditions under which they produce volcanic eruptions. So as an overview of what I'll be presenting in the next 25 minutes, I'll first look at what are these transcrustal magmatic systems and how do we know about them. I'll then briefly look at implications for magmatic processes, and then even more briefly, look at implications for volcanism. So the question, people have been pondering for centuries is, what do these magmatic systems look like? And so one reasonable way or place to look for large volumes of magma is underneath large and young calderas. And I'm going to show you an example from Yellowstone volcano, which is a so-called supervolcano that last had a very large eruption about 600,000 years ago. And there have been several studies of this using seismic methods, and I show you a schematic from a seismic tomography study in 2015. And indeed, using P-wave tomography, you can see that there are large volumes that are unusually slow, meaning that melt is present. But the interpretation is that the upper part of this, big red blob is maybe on average 9% melt, and the lower part is 2% melt. So this study just confirmed and extended a study that was done or published in 2010 that defined or described this magmatic system beneath Yellowstone as being mushy. So that's become a very key term. So I wanted to say, well, what is mush? And from our perspective, mush is a rheological term, and we call it a mush where the crystals are sufficiently numerous that they connect up into some sort of crystalline network so that the rheology or the deformation is controlled by that network. To go from mush to what I'll call a magma, if we reduce the crystal such that, or the crystallinity such that the crystals become disaggregated from each other and are largely surrounded by melt, then the rheology is controlled by the melt. In the other direction, if we increase the number of crystals, we get to a point where the melt, instead of being disconnected throughout the system, becomes isolated into pockets, and I'll call that a rock. And the key thing is that the transitions from rock to mush to magma cause pretty abrupt and large changes in the material properties and the behavior of that. Now, there's another important concept here. When I showed you the tomography studies, remember those 9% melt or 2% melt are averages over very large volumes. But the other key point is that the melt geometry matters. And so if we have melt, if that melt is distributed along grain boundaries, it's going to be very difficult to move around and it will take a long time. So you can't really get it out of the system. However, if that melt segregates into, I've shown here, simplified sills that may or may not be connected, then the melt can move quite rapidly through the system. And in fact, there have been some recent studies that use, again, seismic waveform or seismic waves, but in this case, they're using S waves. And remember that S waves cannot travel through a liquid, and they slow down if there's liquid present. So if you look at the difference in the S-wave velocity as you look vertically versus horizontally, in a lot of these systems, they see quite substantial anisotropy that suggests that the melt is actually segregated into sills. On the left, The Yellowstone, you can see that upper mush region with 9% melt. There's a lot of anisotropy, probably pretty strong segregation into sills. Where you only have 2% melt, there's much weaker anisotropy, and so the melt is probably more distributed. And on the right, I show a similar study by Jack Zabutilov looking under Toba caldera that erupted just 74,000 years ago. So it's the youngest supervolcano eruption. And in that case, their interpretation is that there are just a continuous stack of sills beneath the volcano. More generally, if we look at a place like the Andes or the Cascades in the US, there's growing evidence that you tend to get large accumulations of mush with maybe 15 to 25% melt in the mid-crust. And the most famous and the largest of these is the Altiplano Puno magma body in Bolivia and Chile. But we also see it in the Cascades, and I show my favorite volcano, Mount St. Helens, on the right. In this case, the image on the left was from seismic tomography. The image on the right is a magnetotelluric study. And interestingly here, there's a big mush accumulation, again in the mid-crust. But because of an older batholith, the Spirit Lake batholith, the melt has to get up to the surface to the volcanoes, either by going to the west or to the east. If we look in the upper crust, then we do see evidence of magma accumulations, but only beneath active volcanoes, and they're typically, these magmatic systems are small, they tend to be quite vertical, and they're very transient in time. So to summarize the geophysical evidence, we now think of these subvolcanic systems as dominated by mush, crystal-rich mush, rather than melt. There's evidence that that melt is segregating in places into layers or sills, and we get only localized input into the upper crust to create these transient magma chambers that feed volcanic eruptions. Okay, if we take the next step, let's look at what the implications of these models are for magmatic processes. We know that volcanoes erupt in a diversity of styles and that they produce a wide range of rock compositions. And of course, that's been the subject of petrology for more than a century. In the classic magma chamber model, and all of you who've studied petrology have learned that melts can change composition by separating the crystals from the melt, we call it fractionation, by melting the surrounding crust, and we call that assimilation, or by mixing two different melts together. And in this image that I show, you can see that these purple blobs are coming from somewhere and mixing into the pink blobs. With this new framework of transcrustal magmatic systems, we get a few more things that can be happening. So in addition to the classic ways of changing melt compositions, we've seen that melt can evolve in isolated sills at different depths or pressures, and these can either be tapped directly for eruptions or supply those mysterious purple melts that are mixing with the pink melt. Critically, we're also starting to see that melt composition can change by what's called reactive flow. So as melts flow through this mush pile of crystals, the melts are going to continually react with the crystal and change composition. This is something that's been studied in the mantle for quite a while, but it's pretty new for us igneous petrologists to think this way. And then I'll also show you that magma can include melts and crystals that are assembled from throughout the system. So first, just a quick look at reactive flow. On the left, I show you a tomographic image of mush from St. Kitts. This is from a xenolith that John Blendy collected. And what you see are the different grayscales or different compositions. So the light gray is hornblende that forms the original network. And then you have this network of plagioclase and what was melt, it's now finally crystalline, going through the system. So using tomography, we can image the connectivity of the melt and then actually start to model the permeability. And if we want to understand and model reactive flow, this is the first critical step, is to see how the permeability evolves with changes in crystal content and with the melt structure. If we go to erupted magmas, anyone who's looked through a microscope at magma from an intermediate composition arc volcano will recognize that the crystals are quite varied. I show here backscatter electron images. So again, the grayscale is showing you variations in compositions. This is my sort of favorite rogues gallery of crystals from Mount St. Helens. And you can, just by looking at them, say that they've had very complex and very different histories. And we think that these crystals are being picked up by melt going through the mush pile, and then they're gradually collected together to come out during an eruption. John and I did some work a while ago trying to untangle the history of less complicated crystals in the system. And basically, it looks like the different cores of the crystals come from different places. They have different paths up into the upper crust, but then they're collected, in this case, at about 130 MPa, so somewhere 5 kilometers. And they sit there and grow rims and then are erupted to the surface. Uranium-thorium studies of crystals from Mount St. Helens shows that those cores can be very old, 100 to even 10,000 years. And this is quite common. It's not unique to Mount St. Helens. And also not unique to Mount St. Helens, studies of diffusion profiles show that the crystal rims grew very quickly, over days to maybe years. So we have a huge range of timescales that is not, again, easily explained by classic magma chamber processes, but we can start to understand with this more mush model. I also wanted to show you that melts can also be aggregated throughout a magmatic system. I'm going to show you some examples from Fuego volcano in Guatemala. Fuego is a basaltic volcano or basaltic andesite. It's persistently active, has strombolian eruptions, lava flows, occasional paroxysms, and rare subplinian eruptions. And what's surprising, or was initially surprising about Fuego is if we look at the melt composition that's carrying out the crystals during individual eruptions, we see an enormous range of composition. Shown here is a plot of K2O versus MgO. So huge range in K2O. And from melts modeling, we can show that these vertical lines of K2O change are consistent with practically isothermal decompression. So you take something, in this case, it's about 1,000 degrees, and you decompress it to the surface, and you're getting crystallization during decompression that causes this change in composition. And interestingly, if we look at samples from a subplinian, so a larger eruption in 1974, we see basically the same thing, but mostly that it's moved to higher temperatures for this larger eruption. So, quick summary of the implications for magmatism. We see that crystals are gathered from different parts of the systems and at different times before being transported to the surface. Crystals in the same sample commonly don't share a common history except for the very last stages of rim growth, and that we can also, during eruptions, extract melts from over a large pressure and in some cases temperature range. So just very quickly to end with a few slides on implications for volcanism, which are also enormous. As we've seen, there's growing evidence for very heterogeneous distributions of melt, magma, mush, and volatiles, which Marie will talk more about. And all of these components can move either individually or interact with each other both before and during volcanic eruptions. So we have quite a complex system down there that can drive eruptions in different ways. And I wanted to end, or almost end, with an example of something that I'm excited about because I'm working on it right now with a PhD student, Hannah Buckland. And we've been looking at an eruption that caused Crater Lake in the US. This is a caldera-forming eruption. It was about a VEI 7 in magnitude. And the eruption was immediately preceded by at least one subplinian eruption, an obsidian flow. And then the main phase had the climactic eruption had two phases, one that produced the lower pumice unit and one that produced the upper pumice unit. And it's the person who did this work, Simon Young, assumed or inferred that it was all one eruption. There was just a little pause in between. But if you look at the lower pumice unit, there are two distinct lobes of tephra. So the eastern lobe, the eruption or the tephra went to the southeast, and then the second phase, it went to the northeast. Well, just a few weeks ago, I was on the microprobe looking at glass compositions, and to my surprise, the glass from the eastern lobe, again, has a huge range in composition that is quite different from that of the northern lobe. So this is looking like fuego. And in fact, there was a sort of cartoon published by Wright et al. 2012 for Crater Lake, suggesting that there was a deep feeder system on one side that then fed magma into a shallow, more sill-like lens. And so I'm starting to think that this eastern lobe was fed from the vertical system, and then that destabilized the lateral shallow lens. And progressive disruption of melt lenses distributed laterally has been suggested also for several large caldera-forming eruptions, both in the US, like Yellowstone in this example, and in New Zealand. So to wrap up, I hope I've shown you that the paradigm shift from an upper crustal magma chambers to transcrustal magmatic systems has really changed the way that we view magma storage systems and the conditions that may produce volcanic eruptions. And here I've focused on the melt plus the crystals. In the following talks, Marie and John will extend these concepts to include volatiles, brines, and metals. And with that, I will stop sharing.
Thank you very much, Professor Cashman. So let's continue. There are some questions, but we are going to leave till the end of the presentation. So let's continue with the next presentation. Dr. Edmond, Professor Edmonds.
Hey, thank you very much. So I'll share my screen, which I will do now. Okay, so I hope that everybody can see that that PowerPoint.
Yep. Okay,
so I'm very pleased to be here giving this talk, first of all, and thanks to Kathy for setting the scene so nicely with that first talk. I'm going to be talking about the outgassing of metals from active volcanoes, and this is work that I've done with a few of my PhD students and collaborators here. So let's start with this view of Mount Etna in Italy. Now, Etna is one of the most prodigiously degassing volcanoes in the world. And I think looking at this photo, it's quite clear the role that volcanoes have played over geological time in shaping our atmosphere and cycling volatile elements from the interior of the Earth to the surface environment. And of course, some of these elements are essential for life. They take part in various biogeochemical cycles. Some of them are pollutants. And this plume, you can probably see, is made of a mixture of ash, of gases, and aerosols as well. So here's another plume. This is a different volcano. This is actually the 2018 Lower East Rift Zone of Kilauea. And this is a fissure eruption. So you can see there's the big aerosol and gas cloud. And we took a number of measurements of this. I'm not got time to go through all of the measurements in detail, but this is really to introduce the idea that volcanic plumes contain the species you're probably familiar with, like water and sulfur dioxide, even helium and carbon dioxide. But plumes also contain gaseous species, so species that are present as gases that rapidly condense into aerosols that are trace species as well. So these actually include some of the chalcophile or sulfur-loving metals like zinc, like copper, metalloids like arsenic. We've also got indium, bismuth, and various other metals there as well. So in this talk then, I'll explore to what extent volcanoes outgas these volatile metals, and that includes the chalcophiles, but also the iron-loving elements, the siderophiles. Are they gases or particles? How are they speciated in the gas phase? Does the metal assemblage in volcanic gases differ in different tectonic settings? So between arcs, ocean islands, that's hot spots, and mid-ocean ridges, and if so, why? And then finally, in an attempt to link this talk to the talk that comes after me, how do these gases relate to the magmatic fluids that produce hydrothermal ore deposits? So let's start by looking at the context around outgassing volcanoes. Now, the gas species we measure the most in volcanic plumes, the easiest gas to measure, is sulfur dioxide, because it has a very strong absorption in the ultraviolet region of the electromagnetic spectrum. And this image is an amalgam of various images from space, from a sensor mounted on one of the ESA satellites, showing SO2 clouds from various volcanoes. Now, globally, volcanoes release about somewhere between 20 to 25 teragrams of SO2 per year. And for comparison, they may emit between 50 and 100 teragrams of CO2 per year. And for comparison, this is about 1/100th of the amount of CO2 that humans are releasing through various sorts of activities into the atmosphere. Now, interestingly, this region here in Melanesia, that encompasses Papua New Guinea, Vanuatu, and so on, contributes 1/3 of the global flux of SO2. Now, this same region, which is over here, is also known for its copper and gold deposits. This map shows the largest copper and gold deposits worldwide, and you can see that in many cases it corresponds to presently active zones of volcanism, and those are pink subduction zones shown on there, and also older subduction zones, what we call paleo subduction zones. So those are no longer active. And so there's this well-established link between subduction zones and active volcanoes and porphyry deposits. So in this talk, I'll focus on volcanic degassing and what we can infer from the degassing products about what's happening at depth and the process of porphyry formation. This diagram that was recently published by Park et al. This year shows a hypothetical cross-section of the plumbing system of a volcano. And Kathy has given us a really nice introduction of what might be going on down here in this complex zone in the crust where magmas are stored. And porphyry deposits are forming in the shallow crust, probably at the roof zone of evolved magma reservoirs, which may or may not be connected to active volcanoes at the surface. So let's start the story by explaining how and why volcanoes produce gas plumes. So why and how does degassing occur? So here's another simplified cross-section of a volcanic system. Volatiles are actually very minor constituents of magma. They only comprise a few weight percent typically, and they have a solubility limit. So when the volatiles dissolved in the melt exceed that solubility limit, they tend to exsolve and form either a supercritical fluid at high pressures or a gas at low pressures. And the process of degassing is really caused by two main processes. So during prolonged storage and crystallization in the crust, melts crystallize, and the process of crystallization enriches volatiles in the melt and forces volatiles out of solution. And so this plot at the bottom left here shows the result of a process we call second boiling, which is degassing during crystallization, where basalts evolve to rhyolites, and in doing so, the melt fraction shrinks down to about 5% of the original melt volume. And in doing so, you can generate, up to 10 weight% of exsolved fluids. So this is a way of magmas, possibly over very long timescales, producing an exsolved fluid that may be important for carrying metals. Now, the other way that degassing occurs is under typically much shorter timescales during decompression. And Kathy has mentioned this several times during her talk. Magmas decompress as they rise up through the crust to the surface, and the solubility of these volatiles goes down, decreases. And again, forces the volatiles out of solution. And this is analogous to taking the cork out of a bottle of champagne, decreasing the pressure. All of that CO2 comes out into the bubbles, and that accelerates the liquid towards the surface. So these kinds of processes illustrated on this slide cause the formation of long-lived volcanic plumes at the surface. So how do we measure volcanic gases? Well, many of our techniques actually rely on spectroscopy to measure the main gas phases. But to measure trace metals that we're interested in today, we've actually got to sample the plume directly and pass it through filter packs impregnated with an alkali solution to capture those particles and gases, which are then later analysed in the lab. So this can be done at fixed places in the ground. And shown here, actually, a couple of my PhD students, Penny Weiser and Emily Mason, and Emma Liu from UCL. Or it can also be done using unoccupied aerial vehicles. And just a quick word on UAS or UAVs for volcanoes. These have really revolutionized the way that we monitor volcanoes and make measurements on volcanoes. These are just a couple of examples run by different groups around the world. And you can see that different sorts of spectrometers and gas sampling apparatus can be mounted on these UAS systems and flown really close to high temperature, very hazardous volcanoes, which is something that we absolutely couldn't do before. Now, when we're sampling volcanic gases and aerosols, we can also sample them in a size segregated way using this system of aperture and plates, where the small particles and the large, you can get a size distribution of the aerosol particles. And that allows us to understand a little bit about aerosol growth, residence time of these aerosols in the plume, and how metals might be delivered to the surface environment. And then the trace metals themselves are measured by ICP-MS in the lab. So that's the detail on how we actually do these measurements. Now let's look at some results. So the first big result to report is that fluxes of metals from volcanoes are high and globally significant. And so this bar chart just gives you an idea of the kinds of mass fluxes of metals as gases and aerosols that are being emitted from single volcanoes worldwide. So you can see that we have several tons per day, for example, of copper and zinc being degassed from volcanoes like Etna and from large eruptions of Kilauea. And also cadmium and selenium are degassed in very large quantities from these Icelandic and Hawaiian eruptions as well. Now, these fluxes are not only similar to the anthropogenic flux from entire countries, so that's individual volcanoes equivalent to entire countries, but they're also similar to the flux that we think builds ore deposits in the crust. So these are significant fluxes of metals. Now, we can also quantify how volatile these metals are. And we can do that by comparing their abundance in the plume relative to some element, a reference element, to their abundance in the silicate melt or the ash, or melt inclusions like this one shown in the top right here. These little fragments of melt that are trapped inside growing crystals. And so the gas melt partition coefficient is shown on here. And so elements that show a value above 1 means that they have an affinity for the gas phase, and below 1 means that they prefer to remain in the silicate melt. And you can see from this this plot, all of those elements on the left-hand side up to around gold and indium here show an affinity for the gas phase. Now, these elements are color-coded in terms of their behavior. The ones in purple are the ones that we think of traditional as volatile, so that would be sulfur, chlorine, and so on. The ones in green are chalcophiles, so that's sulfur-loving metals, and they include, of course, copper, and that's the focus of much study, of course, and how fluids transport copper to the sites of copper porphyry deposits, and also siderophile elements, and that includes gold. So these are elements that are iron-loving. So in the earth, they're mainly concentrated in the core. So what happens to these metals when they're emitted into the atmosphere? Well, we've done a number of studies on what happens to them in the environment after they're pumped out into the troposphere at Kilauea and other volcanoes like that. And we find actually, and that's illustrated in this cartoon by this darker grey cloud in the troposphere, so this low cloud here, these metals tend to get, they're present as soluble aerosols, mostly in the plume, and they tend to get washed out or rained out really quite rapidly. So within a few tens of kilometres or within a few days of being emitted from the vent, they tend to get washed out. They either get absorbed or adsorbed onto the surfaces of ash particles or get rained out directly. Perhaps more interesting is what happens to them if they're injected into the stratosphere, which is a relatively dry environment, and they're expected to have much longer residence times here, although there's very little work done on the residence times of these metals in the stratosphere. And in fact, we have done a little bit of work on this very recently. We've had access to an ice core from Antarctica, which has actually allowed us to look deeper into this process of how we might use these trace metals that are degassed from volcanoes to actually reconstruct volcanic records of Antarctica, but also global degassing records that are preserved in the polar ice cores. And this is actually a record of an eruption that took place in Antarctica. So this is a close by eruption from the rift volcano Mount Takahei in Antarctica that happened about 17.7 thousand years ago. And you can see some elemental abundances in the ice here. I won't go into too much detail with this, but essentially the eruption started with an ash-rich phase, which is recorded in these very high concentrations of manganese and light rare earths, and then transitioned into a phase where it was ash poor but aerosol rich. And that's where you can see these really high concentrations of lead and cadmium, thallium and bismuth that are not carried in the ash. They're carried as chloride aerosols and deposited into the ice cores. So there's all sorts of interesting details actually about how long the residence time is of these chlorides, these metal chlorides. And it turns out that thallium might be the longest lived and actually provide a really good record of global volcanism in the ice cores. Now, another big result is that if we measure metals in volcanic plumes from subduction zone volcanoes, where one plate's subducting beneath another, it looks very different, the assemblage of metals, to the metals that we measure in plumes from hotspot volcanoes, for example, in Hawaii, in Iceland, and I suspect also in the Canaries. We may find out this year. So the diagram on the left shows the fluxes of various metals. And again, you can see significant fluxes of copper and zinc, and molybdenum and lead from subduction zone volcanoes directly into the atmosphere. But on the right, we've recast it as a normalized amount of metal, normalized by SO2 in the plume. And we've divided, the blue is the subduction zone data and the red and orange are the hotspot data. And you can see that the subduction zone gases are actually enriched in uranium, cesium, thallium, tungsten, arsenic, copper, bismuth, lead, antimony, that's Sb, zinc, and cadmium, and possibly tin over Ocean Island and hotspot volcanoes. So the question is why? Well, there's two answers to the why question. The first answer is that these metals like to be speciated as chloride. And we know that subduction zone gases, volcanic gases, are rich in HCl gas, hydrogen chloride gas. And on this plot, there's a whole lot of data from my students, Emily's thesis, that shows the chlorine and sulfur ratio on the y-axis of the gas, and then the volatility of the different metal species on the x-axis. And you can see that the volatility of these trace metals is dramatically enhanced when there's more chloride around in the gas. So you can see particularly for zinc, there's a very good correlation between volatility and chlorine sulfur ratio. Cesium, antimony, copper, a particularly good correlation. So these elements are speciating as chloride. So they're being carried as chloride in the volcanic gas. And we can confirm that through thermodynamic modeling. And again, this is work that Emily did. And she used two examples. Villarrica is a volcano in Chile. It's a subduction zone volcano, fairly standard composition. And then, of course, Kilauea is a hotspot volcano. So the top gas contains lots of chloride. And so you can see that some of these metals are speciating as chloride. We've got silver chloride, lead chloride, zinc, and so on and so forth. Whereas at Kilauea, these same elements tend to be elemental or they tend to be sulfides. So there's a significant difference in speciation between the two sorts of environments. So that's part of what's going on. But if we look at the actual rocks themselves as well, the arc magmas that are erupted, and we compare them to Kilauea and Icelandic rocks, we also see that the magmas themselves are enriched in these same elements, so similar elements, over the hotspot magmas. And so there's two stages of enrichment going on here. The magmas themselves are inherently enriched in some metals when they're formed in the mantle, in subduction zones. And then there's a further stage of enrichment where these elements are partitioning into a chlorine-rich fluid. And so that's summarized on this diagram to explain why these elements are enriched in subduction zones. The ones that are coloured in light blue are the ones that have a high slab flux. So they're being transferred from the devolatilizing, degassing slab at depth. And the ones that are ringed in green are the ones that tend to speciate with chloride. And so those two effects actually explain much of what we see in subduction zone gases. So let's just go to a different tectonic setting now, one that you might have in mind when you think of metals and nutrients and biogeochemical cycling. Of course, mid-ocean ridges is where much of the magmatism on our planet is taking place. We all know about black smokers. They've played an enormous role in perhaps even the evolution of life, certainly in shaping the geochemistry of our oceans. So what's going on here with the metals? Well, black smokers, of course, generate a huge array of different sorts of metals. And we've analysed a huge amount of data from mid-ocean ridge emissions. And we've compared the abundance of these elements to a refractory element, neodymium in this case. That's a rare earth element that prefers to stay in the basalt. And we've compared the rock composition to the fluid composition, and we can actually see that some of these elements are vastly enriched in the fluid over the basalt. And these are the ones that tend to be degassing from magma that's underneath the ridge. And these include things like tellurium, arsenic, molybdenum, polonium is there as well, of course. Whereas other elements are not enriched compared to basalt, and these are being actually leached from basalt, which is the traditional, what we think of as the principal process for generating black smokers. This hot seawater circulating around hot basalt leaches out all these elements congruently to form the black smoker chemistry. And on this bottom right plot, you can actually deconvolve these two fluxes and work out for each element whether it's mostly supplied by leaching, which is the y-axis, the hydrothermal flux, or whether it's mostly supplied by magma degassing. And we find that the elements thallium, interestingly, tungsten, rhenium, and tellurium are mostly supplied by magma beneath the surface rather than the leaching process. Now, this immediately has really interesting implications for comparing fast-spreading ridges to slow-spreading ridges, and also looking back over geological time to look at how the ridge flux may have varied over geological time and what effects that may have had. And so there's lots of interesting things to think about with this. And then finally, and this is the linkage point now to John's talk, is how do volcanic gases that I've been talking to you about actually relate to the ore-forming fluids at depth? Now, these are fluid inclusions in quartz on the left here, and measurements of these fluid inclusions, and this is from Guo and Audita in 2017, can derive, again, the affinity of some elements for the fluid over the whole rock in this case. And so this is an enrichment factor, if you like, on the y-axis. So copper, for example, is about 10 to 100 times more abundant in the fluid than it is in the whole rock. And we see the similar kind of trend. So these metals are behaving in exactly the same way in the fluid inclusions, in the evolved magmas. And we see that copper is highly volatile, for example, cesium, lead, selenium, again, highly volatile. And then these elements on the left-hand end are the lithophile ones. So the systematics are the same. And in fact, if we plot the abundance of element X in the plume and normalize it with chloride for these and compare the volcanic gases to the fluid inclusions, we find actually they're quite similar. So on the left-hand column are the low density vapor fluid inclusions found in quartz, associated or not with copper porphyry deposits. And on the right-hand column, those two plots are for brine inclusions in quartz for both mineralized and barren deposits. And the volcanic gas data is the solid black line. So the fluid inclusions is yellow, and the volcanic gases from Etna is the top line, and Stromboli is the bottom line. And we see that in terms of the element normalized by chloride ratio, they are actually very similar, these fluids. Of course, what differs is the bulk salinity of the fluids. The volcanic gases are much less saline than these fluid inclusions. But in terms of the element over chloride ratio, they're very similar. They differ a little bit in their element over sulfur ratio. The volcanic gases tend to be metal depleted on those plots. But I think this shows the importance of chloride in metal transport. And so the final thing to say, of course, is that we can understand this by using this phase diagram. And again, we've got the diagram on the left that shows a central vent degassing at high temperature from basaltic lava lakes and open vents, gives us these high fluxes of metals. But of course, the literature prior to the last 5-10 years or so is dominated by these low temperature fumaroles, which are in fact very metal poor. They're very water rich. A lot of their metal load has been sequestered in the subsurface. And the phase diagram on the right-hand side shows NaCl content of the fluid on the x-axis. This is originally from Lowenstern and Heidenquist and Lowenstern, of course. I should have put that on the slide. And then pressure on the y-axis. And you can see that for saline fluids, they typically unmix at low pressures, forming a low density vapor and a high density brine. And I think these gases that we're sampling from basaltic volcanoes are actually mixtures of vapor and brine that have been advected up from reasonable pressures in the upper crust, in the upper parts of these reservoirs, the lower parts of the conduits, perhaps at 1 or 2 kilometers depth, whereas the fumaroles are really the barren low density vapor end. So there's quite an array, I think, in what we're seeing at the surface, and that provides a link, I think, with the ore fluids. So I'll leave those takeaway messages for a brief moment on the slide here, and I hope that what I've been talking about provides a link with the next talk. Thank you.
Thank you very much, Professor Edmonds. Was interesting presentation. So the last but not the least is the presentation of Professor Jonathan Blundy. So let's continue with Jonathan, and at the end of this presentation, we will start with the question section. Jonathan.
Okay, is that visible?
Yes.
Let's try that. Can you see my screen?
Yes.
Great. Okay. Well, first of all, thank you very much, Paula and Universidad del Norte for inviting me to participate. I'm very sorry that COVID has prevented all three of us visiting your country. I've never been, but I guess this is as close as we'll get for a while. So in the final talk of this little trilogy, my aim is to take what Kathy told us about magmatic systems and what Marie told us about volcanic gases and try to combine them in a framework that might help us as we embrace the transition to net zero, the enormous environmental challenge that faces us in the next perhaps as little as 15 or 20 years. So this talk is really about the green mining part of the title there, from volcanoes to green mining. And I'm going to suggest to you a possible new frontier in resource exploration. That resource being not only metals, but also geothermal power, geothermal energy. So this rather beautiful photograph here is taken by a friend of mine flying over a subduction zone volcano in New Zealand. This is White Island volcano. It's just off the east coast of New Zealand. And it's a volcano that's doing its degassing in the way that Marie described so clearly. And it throws out into the atmosphere, on an average year, 100 tons of copper and 4.5 kilograms of gold. Now, that's not very much compared to Etna and some of the big degassers that Marie talked about. I'll return to those in a minute. But it just gives you an idea that volcanoes puffing away, minding their own business, are delivering to the atmosphere, wasting, if you like, large quantities of metal, in many cases metals that would be rather valuable to us as we embrace the transition to net zero. So let's start with Kathy's talk, really, and I'm going to focus almost exclusively on subduction zone magmas, because that's where most ore deposits of the sort we're interested in occur. So these two plots show some subduction-related magmas from three settings. In grey squares is from the Cascades Arc in North America. In blue diamonds are rocks from the Eastern Caribbean or Lesser Antilles Arc. And in pink dots are rocks from a subduction-related intrusive complex, a batholith in the Italian Alps. And in terms of the elements I've plotted, they overlap, they're very, very similar. And we see an incredible range of chemical composition, from about 45% silica at the low end to almost 80% silica at the high end. And that's the result of a process called chemical differentiation. What comes out of the mantle, what drives chemical differentiation, is almost exclusively at the left-hand side of that diagram. It's basalt, 48% silica. The fact that it can get all the way to 80% silica, that would be a granite, is because it's undergoing chemical differentiation. That is, the crystals that form and the melts are separating from each other. And that takes place in the crust, and it involves what we now call, as Kathy described, transcrustal hot zones or transcrustal magma systems. And this is important from the point of view of ore deposits, because most non-ferrous, that is not iron, metal ores derive ultimately one way or other from igneous processes, from magmatic processes. So we should focus on ore deposits being the extreme endpoint of chemical differentiation. If you like, we start with basalt, and all that chemical change ends up producing something very, very enriched in an element that's impure or a metal of interest. So here are some transcrustal magmatic systems. These are images that Kathy didn't show, but it's the same concept. On the right is something that would be consistent with those geophysical images she showed. This is a system of mush with little lenses that are rather richer in melt than others, shown in green and red. And those wiggly lines show melt percolating upwards, changing its chemical composition by reaction as it does so. The melt eventually accumulates at a thicker layer, that's the red layer near the top of the image. And at that point, it launches upwards. It then reaches sufficient volume that it can actually break through the rocks above and travel up as a dike. And it may go right the way to the surface, or it might stop again and restart the whole process. The image on the left is a cartoon of what's going on inside that hot zone. Not to scale, of course. And it's fueled by basalt from the mantle at the bottom. And as we move upwards, that basalt is changing composition. The color is changing from red to something a little bit more pinky. It's becoming more rich in silica. And it's doing that because the crystals are generally staying behind and the melt is moving upwards, and the crystals contain less silica than the melt. At some point, that's one of those dashed lines that says fluid plus melt, that magma becomes saturated in volatiles. So the initial load of water, carbon dioxide, sulfur gases, halogens and so on exceeds the solubility at that pressure, and little bubbles form. Those are the blue dots. And those bubbles now start to move upwards, and those are the blue arrows. So in this very dynamic system, we have green arrows, that's melt moving up, and blue arrows, that's fluid or gas moving up. And they've become decoupled from each other. So these mushes are very efficient ways of separating out the phases. The gases come out the summit, the volcanic edifice, as Marie showed, and the magmas may also come out the edifice as an eruption, or they may get stuck and form a pluton. Now I'm going to focus on the top part of that diagram. I'll return to what those words brine and lens and supercritical fluid mean in just a moment. So key points are that differentiation here is taking place by percolative reactive flow. That's a rather different process to something more traditional like fractional crystallization that is more familiar. Fluids, melts and crystals are decoupled. They have different physical properties. They travel at different rates through the system. We've heard from Marie that fluids are very important for metal transport, especially if they contain the chloride ion or chloride ligand. And many magmas are actually quite rich in fluids, particularly water, but also carbon dioxide and sulfur species. And those first bubbles, the first fluid saturation, may occur quite deep in the crust. Okay, so now let's take this through to a conventional ore deposit related to subduction magmatism. Most, about 3/4 of all copper comes from porphyry copper deposits, and of that about 2/3 comes from Chile. Other big porphyry copper deposits are mostly around the Pacific, but not exclusively. This is a cross-section through a porphyry copper deposit that's actually in the Basin Range province of the USA, in Nevada. And I show it because faulting means that this vertical section, shown here, is actually a map. So the tilting means that the top of the section lies in the west and the bottom of the section lies in the east. And you can walk the ground and make a map that's actually a cross-section. And we won't go into any great details here, but the point is at the surface, labelled there domes, were once volcanoes, and down at the bottom were bodies of magma, labelled granite. And the region in between those two is where fluids are coming off the granite and they are making their way to the surface, and on the way they're reacting to produce ore deposits, mostly copper, a little bit of gold. And so all of that ore mineralization is associated with fluid conduits that connect, if you like, Kathy's part of the story and Marie's part of the story. And if I put an ore deposit on there, it would sit right in the middle, somewhere in that top of the magma, transcrustal magma system, but below the volcanoes. And obviously what goes on in that region. This is a big mine in Chile called Cerro Colorado. We can get insights into that by looking at the volcanoes up above and the granite rocks or the bits of plutonic rock brought up by volcanoes. So ore deposits sit right at that sort of confluence of the plutonic realm and the volcanic realm. So let's take this into a real world situation. Petrology is very interesting and it tells us a lot about how volcanoes work, but I want to see whether we can actually use petrology to help us resource the low carbon transition. So as we move on some time scale, perhaps by 2035, perhaps by 2050, perhaps never if we're very unlucky, as we transition towards a low carbon economy, demand for certain critical metals will increase dramatically. By critical metals, I mean those involved in electric vehicles, EVs, photovoltaics, those are PVs, all kinds of power generation. We will suddenly become hungry for all sorts of metals. Recycling will help, using less will help, but we cannot get there just by recycling and using less. We are going to need new resources, and we'll need them rather urgently. So one option is business as usual. Let's have some more big mines. More mines, more metal. We can drive the transition that way. There are a couple of problems there, really. One is big mines aren't that easy to find. And the second is we actually want to sustainably extract the metals. There's not much point in turning to electric vehicles in one part of the world, but generating a lot more carbon dioxide somewhere else because we're mining more. The kinds of metals we need, I can make a long list of critical metals, but the list on the right, I've just highlighted two that are of interest. One is copper and the other is lithium. Copper is used in a lot of electricity generation and transmission, and lithium is used in batteries. So let's just think of copper. I showed you an ore deposit snapshot in the last, a cross section in the last slide. So a copper mine, this is Chuquicamata in Chile, one of the biggest. A copper mine is a big hole in the ground, in this case 4 kilometers long, 3 kilometers wide, and 1 kilometer deep. When you look into Chuqui, it's very hard to get a sense of scale. Let me tell you that a giant truck is too small for you to be able to see in that image. Then there's about 65 megatons of contained copper in there, but the grade of the ore is really low. Less than 1% of that rock is made of copper. That means that when it's mined, 99% and a little bit more is just thrown away. It forms a tailings dam at the surface with all sorts of attendant deposits. Let's contrast that with Marie's wonderful data that are shown in the image on the right. This is a really big degassing volcano, Mount Etna in Sicily. Now we're looking at kilograms a day, and let's just focus on copper on the right there. 20,000 kilograms a day, 20 tons of copper a day, lost to the atmosphere. And there are lots of other interesting, attractive metals for the green economy, green tech on the right there. Bismuth, cadmium, arsenic, lead. There's also precious metals like gold and silver. Wouldn't it be wonderful if we could harness that volcanic flux? We could get the metals out of volcanoes without having to do that bit on the left where you dig a big hole. Right, so let's go back to basics, and let's apply this transcrustal magmatic system to see what it can tell us about forming ore deposits. So this is a volcano high on the Bolivian altiplano called Cerro Uturuncu. It's just over 6,000 meters above sea level, and the plateau there, the altiplano, is about 4,400 meters above sea level. Now, Uturuncu sits above that very large, partially molten region that Kathy talked about, that we call the Altiplano Puna magma body, and this is an electrical resistivity image, and the red colours are low resistivity or high conductivity. They're a region where there is a conductive material. And down in the APMB, down at 15, 20 kilometers or more, That conducting material is partial melt. It's sitting on grain boundaries. It's probably 10 or 20% by volume, and it's got a lot of water. We see little tendrils of conductivity rising up. They're conductive bodies labeled C. You can see C3 and C4 and C5 and so on. And these are also conductors. But there's a challenge here, because Uturuncu, that you see there, has not erupted for 250,000 years. So those conductors under Uturuncu, let's focus on C4, very, very unlikely to be magma. This is a volcano that, to all intents and purposes, has stopped erupting. However, it is actually a very dynamic place. The image on the right is based on satellite imagery, satellite interferometry. And it actually measures the rate at which the ground is moving, the vertical displacement up or down. And Uturuncu is the center of the red target there, and it's going up in this time period at about 6 millimeters a year. And there's a moat around Uturuncu, about 50 kilometers out, that's actually going down. And the reason Uturuncu is going up and the moat is going down is not because Uturuncu is about to erupt. It's because fluids are being discharged from that APMB and are rising up and inflating the region under the volcano. And the reason the footprint of that uplift is so broad is because the source of the deformation is very deep. It's in the APMB, about 15 kilometers down. And so even though Uturuncu is not erupting, we see evidence of these fluids at the surface. We see fumaroles, they're not really hot. We see some steaming on the left there. And there's actually quite a lot of sulfur associated with some of them. You see in the picture on the bottom left. So the most likely explanation for the crustal conductor at Uturuncu, that's the U in this picture, is actually a different conductive material, not partial melt, not magma, but actually a salty fluid called brine. And when I say brine, I mean something that's about 10 times saltier than seawater, so about 40% by weight NaCl, and quite a lot hotter. It's a magmatic brine. And what's rather remarkable is that conductors like the one shown under Uturuncu exist beneath every single volcano that we looked at. So there's another example up at the top. This is in Japan. That's actually where I'm speaking from now. Again, we see a deep conductor that's thought to be melt, but a shallower one that is labeled brine. And in most of these systems, there's a very shallow conductive layer that's actually just smectite clay. So we have a deeper melt, a brine that's at a depth of a few kilometers, 3, 4, 5, and then clay right at the surface. And the formation of the brine is a byproduct of the volcano degassing, or the magma degassing process that Marie described. And in her penultimate slide, she showed the all-important phase diagram. And just for reference, we're a little bit deeper here than most geothermal systems, but I'll return in a minute to the implications of these brine lenses for geothermal processes. So, to make a brine, you need chlorine, and we need to wonder, how do we get chlorine into the magmatic gas? Most important volatile in magmatic systems is water, and then CO2 and sulfur are also important constituents. Chlorine is not such a major component, certainly not 40%, but it does partition into fluids as magmas degas, and the partition coefficient shown in that top slide, that's how much goes into the fluid divided by how much goes into the melt. So a big number means it's going into the fluid. Depends on the pressure and also the type of melt. I won't dwell on the diagram, but obviously where you're degassing and what the magma is influence the chlorine content. When I say NaCl, it's a useful way of expressing the chlorine content. Hydrogen chloride or hydrochloric acid is also present. The chlorine can be complexed in different ways. The 3 panels below show the degassing of Mount St. Helens volcano in the Cascades that Kathy talked about. And the details aren't important. Little droplets of melt inclusions show the red dots, and we see that actually the chlorine is remaining roughly the same as the pressure goes down, but the fluid composition is changing. Those are the lines on the right. And the only thing I want you to notice is that the fluid that's coming off has a salinity up to about that of seawater. So it's not super salty. To get to super salty, we need another process. So most volcanoes release a fluid that's 4-8 weight% sodium chloride. Very rarely they produce brine straight away. To make the brine, we need to decompress the fluid, we need to change the pressure. So the top right-hand diagram, which is the same as the one that Marie showed, but without the logarithmic scale, is a phase diagram for the water NaCl system. So NaCl is on the right of that diagram, and water is on the left at 0. And if we put a fluid and drop with say 4% NaCl, that's the blue line, and we drop the pressure, it starts out in a supercritical state. That's just a single phase. It's not gas and it's not liquid, it's a fluid. But as it reaches one of those black lines, it starts to separate, undergoes phase separation. And the left-hand limb of those lines defines vapor. Let's call it steam. It doesn't have much salt, it doesn't have much of anything in it. And the right-hand limb is the brine. And you can see that's at 40, 50, 60% NaCl. And the phase separation depends on the temperature of the gas. So we can simulate this process. We can create hydrodynamic models where we take that blue arrow, that supercritical fluid, and we pump it up a volcanic conduit, and that's what the cylindrical image shows on the bottom left. So there's a conduit that has relatively high permeability beneath a volcano, and the red arrow shows us pumping 4 weight% NaCl fluid at 750 degrees up that conduit. And the conduit is in some slightly lower permeability country rocks. As the fluid ascends, it undergoes phase separation. And the brine is rather dense and gets stuck. And out the top comes the vapor. And the brine spreads out laterally and forms what's called a brine lens. And the snapshots on the right show the brine lens geometry, the shape, 1, 5, 20, and 250,000 years after degassing started. And these are axis symmetric images, so you can just rotate them around the horizontal axis. And the red blob has a high salinity, that's the brine lens. And you see it spread out and sink slightly as it forms. And you see the depth is 2-3 kilometers, just the same as those conductors we saw in the last slides from the electrical conductivity surveys. And the depth is largely controlled by the phase diagram on the left. You can see that when we turn pressure into depth in that diagram on the left, we end up with the same depths as the brine lenses on the right. And these brine lenses are very long-lived. Once they're formed, the only thing that can really destroy them is slow erosion by groundwater, which is why on the Altiplano, where there's not a lot of groundwater, the brine lens under Utarunku has been there for 250,000 years. Right, so why does this matter for metals? Well, as Marie explained, metals, almost all of them, just love chlorine or chloride complexes. They readily form complexes in the fluid if there's the chloride ion around. And this is a plot showing the partitioning of copper between fluid, F, and melt, M. And a big number means it's really going strongly into the fluid. And the logarithmic scale on the bottom shows how salty the fluid is. And you see that as the fluid becomes more salty, more chlorine rich, so the partition coefficient goes up. The relationship's a little bit complicated, but more salt in the fluid, more copper goes into it. So when we form those brine lenses, the fact that they're very salty means they just suck out or sequester all of the metals that were in the original fluid. So what we see is those fluids that are being discharged at the surface that Maria's analysed are often the depleted part of the whole fluid metal system. The bulk of the metal gets stuck underground. So we can take the same hydrodynamic models and we can calculate how much copper or any other metal could be trapped in one of those brine lenses. So we do lots of degassing scenarios. We do fast degassing, slow degassing, hot, cool, very permeable, less permeable, lots of groundwater, etc., etc. We run thousands of simulations and we calculate how deep the brine lens is and how much metal it's got in it. And that's the panel on the right. And it shows that the brine lens is almost always at the same depth, and in some cases can contain 16 megatons of copper. That's a lot. That's that big copper mine in Chile that I showed earlier, about 20. So 16 is an amount of copper worth getting out of bed for. But it's called copper potential because that doesn't mean that that's the amount of copper that's contained. That's the amount that could be contained if we are controlled only by the solubility of copper minerals. So the plot on the left is how much copper you can dissolve versus temperature for 3 different salt contents. Very salty, 40, less salty, 10, and seawater, 4. And 2 things stand out. One, the saltier the fluid, the more copper it can contain. But the other is that the hotter the fluid, the more copper it can contain. So the most juicy brines in terms of metals are hot and salty. As they cool, if there's reduced sulfur or sulfide around, they actually start to dump out their copper as the form of copper sulfide, chalcopyrite. So let's see what real fluids look like. We could look in ore deposits or we look in geothermal systems. And those various little bars you can see on the left-hand diagram are fluids we've analysed from 3 different volcanic or geothermal systems. And I'm just going to talk to the one that's in orange. It's called Kakonda. This is a remarkable place and is actually the reason that I'm currently in Japan. So Kakonda is a geothermal system. It's located above a young granite. And when I say a young granite, I mean 90,000 years old granite. And it was drilled in the 1990s for its geothermal power, geothermal energy. And it was drilled to 3.7 kilometers to a temperature of 520 degrees in 1995, which is a pretty remarkable feat. And the many drill holes are shown with the vertical lines. And what I've done is I've taken the cross section where you can see written granite, reservoir zone, dacite, and I've superimposed on that the electrical conductivity, and pink means conductive. So the most pink region under the word granite is where the rock is very conductive because there's brine present, just like under a Turunku. In this case, the brine is probably present at about 5 to 8% by volume. This granite is associated with volcanism, not that particular intrusion you see there, but there probably were volcanic rocks associated with this at some time in the past. And the geothermal reservoir, the conventional geothermal reservoir, is where it says a reservoir zone. That's where most geothermal power is extracted. And you see the temperature there is between 300 and 350. The amazing thing about Kakonda is they drilled right down into the granite, not quite into the most brine-rich part, but down to depths of 3.7 kilometers. And we have samples of the borehole, those are all those KK samples, from right at the bottom up to a depth of about 1.5 kilometers. And what we did is we took crystals of quartz out of the rocks, out of the drill core, and we analysed the tiny fluid inclusions. That's that image on the right, little droplets of trapped fluid. And we analysed them not only to determine their salinity and what temperature they formed at, but also to see what metals they contain. So this is a real test whether those brines that we've hypothesized could contain metals, do they actually contain metals in a real system? Well, the first thing we did is determine what temperature they record. And they record temperatures up to 500 or 600 degrees, so that's very promising. And the deepest well is the bottom, and deepest sample is the bottom, and the shallowest at the top. And you see the temperature decreases upwards, as we'd expect. And you can just about read those small figures. The salinity is about 50 to 60%. So far, so good. And if we superimpose on here the temperature in the well today, we see a pretty good correspondence. So the fluids that are trapped in quartzes are probably the real fluids that are in the reservoir today. And I will demonstrate that in just a moment. So we're looking at real modern metal-rich reservoir fluids. I say metal-rich, how much metal? Well, here are all the metals. So let's just get a head around that diagram. We go from deep on the right to shallow on the left. And the different metals are in boxes with the chemical symbol. And 1 weight percent is the horizontal line. This is 10,000 parts per million. We go up to 2.5 weight percent zinc. We go up to 1 weight percent copper. We have typically around about 50 to 80 parts per million silver. We have lithium contents approaching 1,000 ppm. We've got a huge diversity of metals, all in those fluids. Overall, the metal endowment is higher on the right-hand end of the diagram, and it decreases towards the left, as you might imagine. And if we look at the rocks themselves, on the right, we have granite, that's supplying the fluid. And on the left, we actually have some ore zones, some mineralized zones. Those are crystals of sphalerite and chalcopyrite. We have other insights into what's in those brines, because we actually have samples of brine. The drilling that they did in 1995, they actually recovered some brine from 3.7 kilometers down. And that's what I've labeled well-bore fluid. And also, in most geothermal plants, metals that are in solution precipitate out on the walls of the pipes. These are called scales. And the image in the top left is a section through a pipe, actually from Greece. And all that brown, white, grungy stuff is actually scale. It's precipitate from the fluid. And in the diagram on the right, those are shown as the grey bars. And finally, the purple symbols are the analyses of the fluid inclusions. And I've shown a dozen metals there, from zinc on the right to gold on the left. And all I want you to notice is that the scale composition, the well-bore fluid composition, and the fluid inclusion composition are broadly similar. So what's coming up the geothermal well, what's oozing out at the bottom of the hole, and what's trapped as fluid inclusions is the same brine. This is an ore. It's a liquid ore, and can we get it out efficiently? Most of that ore is actually silica, in fact. I haven't marked that, it's not a very interesting metal. And the scale comes in the form of sulfides and sulfates and carbonates. And if you were to talk to a geothermal engineer, they would describe that as a massive nuisance because it reduces the productivity of the well. If you were to show those same scales, the stuff in that pipe in the top left, to a miner, the miner would say, wow, high-grade ore. So it's an interesting paradox, really, that a material that is very rich in metals, sufficient to be an ore for a miner, is actually a problem for a geothermal engineer. The challenge with green mining is to get all of those metals in the bottom right-hand diagram up to the surface and out at the same time as geothermal power. And this is the concept of green mining. And it's something that we propose could be used to try to tackle the impending demand for critical metals. So here are some of the benefits. We know that brine lenses are ubiquitous, so it's much easier to find a volcano than it is to find an ore deposit. We can hunt for them very easily using geophysics, magnetotelluric or seismology. Not only do we get metals, we can also have geothermal energy. We can use the geothermal energy to power the processing at the top of the well. So we can go zero carbon in that sense. Unlike typical mines that may produce a few metals, lead and zinc, or copper, or gold, or molybdenum, brines have this huge range, this polymetallic endowment, base metals, critical metals, and precious metals. Sinking a hole down to 2 or 3 kilometers does not require an open pit, and it doesn't require an awful lot of waste rock at the surface. You might think this is a challenge to get down to these depths. Well, it was done in Japan in 1995, and drilling to these depths, accessing these high temperatures, is very much the new frontier of supercritical geothermal power, with pilot operations in Japan, Italy, New Zealand, Iceland, Mexico, and the United States. And that final bit of the jigsaw puzzle, how do we get the metals to the surface without them sticking to the pipes? That's going to require some research into novel materials, functional materials synthesis, so that rather than forming scale, we actually transfer the metals to the surface where they could be harvested. So that's the concept of green mining, and I hope in our 3 talks we've taken you from igneous petrology through volcanology to economic geology to show how all of these fields are connected and perhaps might even be very valuable as we approach probably one of the biggest challenges that humanity has ever faced. Thank you for your attention.
Thank you very much, Professor Blundy. It was very interesting presentation. So let's start with the question section. I think we have a lot of questions from the students. So once again, I would like to thank you to be here and share your knowledge and your studies about the magmatic system and volcanic system in order to develop mineralizations. So I have the first question, will be my question. I was thinking that there is a difference between different magmatic environments and tectonic environments as well. So if we compare, for instance, if we just think about the subduction zone associated to the South America, do you think that could be difference between the subduction zone at south of South America, central part and north part of South America, in order to develop different kind of deposits? We can map, for instance, the South America deposit could be more associated to more bigger copper deposit than North or Andes or Central Andes. And we can connect this with the difference in volcanic activity.
Want me to start?
Go ahead.
No, I was just going to say that one very obvious difference along the margin of the Americas is the duration of subduction and the age of the subducting plate. So up where Mount St. Helens, where John and I were talking, then the plate that's being subducted is quite young because it's just coming from the Juan de Fuca Ridge offshore. And the magmatic arc itself is quite a bit younger than, say, the Andes. And so the result is the Andes, you have this hugely thick crust. And then in Central America, you've got places like Nicaragua where the crust is very thin. So there are big differences in the subducting environment just because of the age of the plates and the thickness of the crust. And then I'll hand over to the other two what difference that makes for ore deposits.
Well, I think the big question, Paula, and is the important thing, and none of us fully addressed it, I guess, is the important thing with ore deposits what you put into the subduction zone. So what's on the plate that's going down? So is it the source, or is it actually the process? Is it something to do with the way those metals are released in gases or stored in brine lenses? And I don't know, Marie, has anyone surveyed the gas chemistry all the way along from you working in Villarrica all the way up to sort of British Columbia? Do you see changes?
Yeah, I mean, you see changes related to the thickness of sediments going in, for example, for the carbon budget. And you also see differences in degassing style, so in fact, Kathy and I have been working on a paper recently trying to understand why some volcanoes degas huge amounts even between eruptions and what actually sustains that degassing. And that's an interesting question, whether these volcanoes can also sustain the formation of long-lived ore deposits or accumulation of brines at depth at the same time. And we think that may have something to do with tectonics, because all subduction zones, they're not all compressional, of course. Sometimes the upper plate can be actually extending, and that can create accommodation space for very large fluxes of magma to come in to sustain this very large flux of fluid through the upper plate. And that's manifest as prodigiously degassing volcanoes, but also potentially, large brine accumulations as well, as I was talking about. So I think that's an interesting aspect too.
Yes. Okay, so let's continue with some questions in the chat. So the first question was the Stephanie Buitrago question. She asked, what other condition can generate changes in the melt compositions? I think that this question was about the Professor Cashman presentation.
Right, I'm not sure what she means by other, because I gave several examples of both the classic examples of or traditional explanations of fractionation, pulling crystals out, changes the melt composition, assimilating, melting some of these wall rocks around, you can change the composition, or mixing melts together. But as I said, one of the things that I think John and I are particularly excited about is to think about this new mechanism. So in addition to those three, just what's happening as the melt is going through these big crystal piles. And then not just the melt reacting with the crystals, but as Marie said, there are also volatiles that are streaming through these mush piles. So they're all going to be interacting with each other. And so I think that's something that we're only just starting to think about in terms of how important that is for affecting the magma compositions.
Yes. For instance, if we compare two magmas, and one magma which is hydroxide and fertile, another is sterile magma, which will be the difference in the petrographical signature that we can differentiate hydrotrophic and fertile magma versus sterile magma?
Well, that's
one question.
When you can answer that, you can make an awful lot of money. There are a number of interesting things, though, Paula, for example, many of the biggest ore deposits in Chile, they're called porphyry deposits because they're associated with dike rocks that have a very characteristic texture. They have lots and lots of crystals in a fine-grained matrix. And often the proportion of crystals seems so high that it's surprising the magma could ever flow. And what we think happens there is that they're a product of very, very volatile, rich magma. So the crystals weren't originally that close to each other. They were separated by a lot of gas. And to get all that gas into the magma, you have to start very deep. And I think, as Marie mentioned earlier, if you have a magmatic system and then you stretch it, you can start to get stuff out, not just from the top, but actually from very deep. And then under those conditions, there's a lot of gas, a lot of dissolved volatiles. Chlorine goes very readily into the fluid, and you may be able to bring up these very volatile, rich magmas that produce a very characteristic porphyritic texture. So,
and I guess the interesting thing is that, you know, we certainly talk about a lot, is under what conditions does that just set up a system where all your volatiles and metals go shooting through, and you know, do you sort of send them out the top, and under what conditions can you actually trap them and concentrate them? So I think that's the key question, because you know, you need a lot of volatiles going through, but sometimes they go all the way through.
Victor Petit make a question. He asks, do minerals accumulate in the magma in some specific way, or that will happen randomly? I mean, a specific way, maybe in a specific area, or
yeah, I think again that's a really interesting question. For a very long time, you know, we worked under the model that you have crystals settling out. So then the heavy crystals like olivine go clunk down to the bottom, and the lighter crystals like plagioclase would stay on top. So there was a systematic, and this certainly happens in some cases, like the big famous layered intrusions. But as I tried to show, as our tools have developed so that we can really analyze individual crystals, I think in these arc systems, often the crystals just seem to have been plucked from throughout the you know, quite a large vertical area. And so in that way, I think it may be a little more random. I don't think we can answer yet whether there's a system to where things are being incorporated from.
Yeah, thank you, Kathy. Professor Blundy, do you think that there is a relationship between the amount of metals into the deposit and the relationship with the amount of fluid inclusions in the minerals, for instance, in quartz or something? We can map the relationship with the amount of fluid inclusion and the amount of metal.
Well, it's a good question. You'd imagine the more fluid inclusions, and you'd imagine that the more fluid, perhaps the greater its ability to transport metals. But I've certainly never looked at that. Some of these rocks that I described from Japan have thousands of fluid inclusions. It's not a problem finding them. On the other hand, if you look at most volcanic crystals, as Kathy and I have tried to look for fluid inclusions at Mount St. Helens, there are fluid inclusions, but not thousands.
Yeah. And they're also tiny. They tend to be too small to analyze.
Because it will be a relationship between, for instance, if we see we compare the fluid inclusion associated to porphyry deposit or epithermal deposit or mesothermal deposit, the fluid inclusion, the size, form, everything will be different, no? And the amount as well. I think the dry head, for instance, if we compare the high grade zone between low grade areas, the amount of fluid inclusion will be higher in high grade zone. Do you think that?
I have to say I've never looked at the number of fluid inclusions. I think I'm always glad when I find one, but I'm not sure. I've never actually counted it. You've made me now wonder if I go back to Kakonda and see how does the number of fluid inclusions per gram of quartz change up that section.
Yes. Sorry, somebody.
I was just going to say that we've thought about this with melt inclusions too, but no one has ever really done a systematic look at why melt inclusions form and what specific conditions trap them. And I guess with fluid inclusions, there are fractures going through where you get a lot, but there are also isolated ones. And so I think just asking questions, not only about what they contain, but how they form is probably really important.
Yes. Fanny Guzman, maybe this question is for Professor Edmonds. She asks, how often do you monitor this volcano? You talk in your presentation about the monitor in order to take some gases and so on. So how often do you monitor those?
Yeah, well, that's a great question. And I suppose the answer is it's highly variable around the world. So usually for monitoring purposes, we just look at SO2, the easy to measure gases, and SO2 is the easiest to measure gas, sometimes also CO2. And these are proxies for the total amount of gas coming out of a volcano. And many volcanoes have ground-based networks. So for example, Etna, and many other volcanoes around the world, White Island, the picture that John showed in his talk, has a network of ground-based spectrometers that scan through the plume, measuring the flux of SO2 every few minutes. But the great advantage we have now, of course, is we can observe the Earth from space, and we can actually see even those regions which don't have the resources to have their own ground-based networks, Papua New Guinea and so on, and bits of Indonesia, for example, we can actually observe the whole thing. So we can get really good idea of how fluxes are changing in different places. The key thing is to try and get the high spatial and temporal resolution to allow you to see changes that might actually feed into forecasting eruptions, which need more detailed scrutiny. But I suppose the answer is it's increasing all the time, and we have quite good coverage now.
Okay.
Yeah. Well, just one more note. So we had a master's student a few years ago look at the development of monitoring networks in several different countries, and particularly in relation to critical eruptions. And one thing that really jumped out is Colombia, had virtually no volcano monitoring until Nevada del Ruiz, and since then it is one of the best countries for volcano monitoring. So Colombia was very impressive in their response to what was obviously quite a terrible disaster.
Yeah. Sharon Rodriguez asks, can a volcano turn from barren to fertile magmatic system? From the sterile to...
Absolutely. So what's quite interesting, that's a very good question. If you look at some of the big ore deposits in Chile, they have a lifetime perhaps of several million years. And there's normally a steady increase in fertility, and the most fertile magmas come at the end of the lifetime. So I'm not talking about the volcano now, this is actually the ore deposit, but if you imagine the magmas that fuel the intruded where the ore deposit is, they become more fertile with time, and if I plotted fertility versus time, they go up very suddenly. So the most mineralizing event, the richest event, is right at the end of a magmatic cycle. Then it drops and the system has to build up again. So it's as though the metals are accumulating in the system, and then something happens and they all get sent up to the surface.
Another question. Oscar Orozco asks, what impact do gases emitted by volcanoes activity have on the environment? What is the volcanoes emission impact the environment associated with different kind of elements?
Yes, so obviously some of these metals that we've talked about today are highly toxic, and we've also emphasized that they're delivered to the surface environment in soluble form, and that means they're really easily taken up by plants, they're easily incorporated into the hydrological system. So for low-level volcanic plumes that are persistent degassers, emitting high fluxes continuously into the lower part of the atmosphere, this can be a significant problem. Elements like thallium, arsenic, mercury, lead, and our work at Kilauea has shown that these get typically washed out of the plume quite quickly, and that means that people that live very close to volcanic plumes, that there should be, and there is in many cases, but monitoring of the hydrological systems and biosphere and so on, because these are significant impacts. Of course, the larger explosive eruptions, which emit emissions into the stratosphere, have much longer range and longer timescale impacts. And it's not clear that metals have a significant environmental impact in that sense, although, of course, sulfate aerosol has the impact of lowering global climate if the eruption is big enough. For example, after Pinatubo in 1991, there's a 0.5 degree of global cooling, just lasted a couple of years afterwards. But the metals, we just don't have much data on how the metals behave in the stratosphere. But certainly in the lower atmosphere, it can be a big impact on the environment.
Associated to the last eruption for La Palma volcano in Canarias, this volcano actually has some important elements in order to extract or for mining or something like that. What kind of element have you studied that volcano, and understand what kind of elements are associated?
Yeah, well, the answer is not yet, but hopefully there will be data, because I know one of my colleagues has been out there to do some measurements. But we'd expect this sort of volcanic plume to be very similar to Hawaii and Iceland type eruptions. So presumably we're going to see that it's very rich in the very volatile metals like selenium, tellurium, rhenium that we also see in Hawaii and Iceland, and perhaps slightly less rich in the elements that we know are transferred from subducting slabs. Although we can never predict these things with any certainty, and it might turn out that there is a bit more complexity, but we'll wait and see. But that's what we'd expect. I mean, these kinds of eruptions, interestingly, are very similar to the very large flood basalt eruptions, of course, that have happened all the way through Earth history. And so they're interesting to study from that perspective as well. What sort of impact these volatiles, including the metals, might have had on the environment during, very big eruptions that were associated with mass extinctions in the past.
But of course, the big immediate impact from an eruption like this is the sulfur content, the SO2, and that large, long-lived eruptions like the Laki eruption from Iceland in 1783 put out so much sulfur that then, or H2S, that then gets oxidized to SO2 and then to sulfuric acid, and it caused a lot of problems in Europe from acid rain. Now, an interesting thing about that, which would also apply to the Canaries, is that oxidation event is triggered by sunlight. So it happened that the Laki eruption occurred in midsummer, where there's like 24 hours a day of sunlight in Iceland, whereas the Polaron eruption that happened in 2015 occurred mostly over the winter. So there they had local problems with SO2, but they didn't see distal problems with sulfuric acid. But La Palma presumably has lots of sunlight. So yeah, I don't know if they've been watching acid plumes or had acid rain problems.
Yes. Okay. Well, we'll finish the question section. And we would like to thank you once again for accepting our invitation to join us this virtual section in our Cátedra Europa. I think the three presentation was amazing. That there is a lot of ideas in order to start working with this. I don't know, new, or I don't think that's not new, but I start working with this in North University and also in different universities here in South America and Central America. So thank you again, all of you, and also for the audience. And so So let's, Anthony, continue with to finalize the presentation. Thank you, guys.
Thank you.
Well, thank you. Someday we'll come knocking on your door in Colombia.
Yes,
In
please.
the post-COVID world, hopefully.
You're welcome to come.
We thank our guests for their special participation and all attendees for joining us in this session of Acceder Europa. We invite you to continue supporting the education of talented students through our scholarship fundraising campaign, Más Becas, by clicking on the donation button on the homepage of Acceder Europa. We also encourage you to stay connected to the rest of Acceder Europa events. Thank you.